the next speaker is my dear supervisor, Mr. Izzet SAKALLI. You already know him from yesterday.
So I have to set up my computer. Okay, actually, in the standard program, I don't have any speech, but later on, the problem happened to one of our speakers, and I was a substitute member of this organization. Today, I'm going to talk about one of the papers that we published. Another PhD student, who will be the next speaker. This paper has been published recently in Physics and Neumann, which is entitled Spectroscopy of Rotating Linear Dilaton Levels from Boxed Poisson Orbitals. First of all, I will give a brief review about the quantization of black holes. Starting from the Wittgenstein, I will make a brief review about the quantization, how the black holes can be quantized. Then, from the new definition of the Poisson ones, which is called boxed Poisson orbitals, which is the name of the Shahar Hots from Ruben academic from Israel. We follow one of his study and generalize it to the rotating ones. Then I will also give introductory knowledge, introductory information about the rotating linear dilaton space-time, and its corresponding Zerelli equation, which is a one-dimensional Schrödinger-like wave equation of the massless-like Gordon equation. Then I will also show how one can compute the box Poisson orbital by using the particular boundary conditions. And finally, using the Wittgenstein conjecture, we will show how the area and the entropy can be quantized, how they are equally spaced for a considered black hole. Nearly 2 years ago, unfortunately, we lost the Wittgenstein. That was also one of the breaking news in the New York Times. If you want to learn the insights of the black holes, according to me, you should read the articles of Hawking and then the Wittgenstein. And you have to go back to the 1970s, especially the one which was published in 1974. It was showing quantum mechanically that the minimum possible change in the horizon area of a black hole is a constant number, which is 8 pi h bar. And it is independent of the characteristic of the black holes. It doesn't important what kind of black hole you have. That should be the minimum change. But this is a conjecture. Somehow that result is based on the FFS theory. That FFS theory also was used in the Bohr atomic model. You know, from the modern physics books, we have Rutherford model, and then we have many atomic models before, but the most reliable one was the Bohr atomic model. And over there, the energy is quantized. So even that was used the FFS theorem because any classical adiabatic invariant corresponds to a quantum entity with discrete spectrum. I mean, if you're in a phase space, the areas that you got should have a discrete structure. And the first time after the Wittgenstein, the Constater, in his PRL paper, he also studied on the quantization of black holes, and he reformulated the adiabatic invariant for the black holes. The E over there is the total energy of the black hole system, and the omega is the frequency emitted from the black hole. what he did, he used the quasi-normal modes. By the way, you may ask me, what are these quasi-normal modes? Maybe from even our daily life, you know that if I knock something here, just getting listening to the noise, you can guess what type of material that I knocked, whether it is wood, plastic, metal or not. So these are the characteristic sounds, because so black holes also have the characteristic sounds which are called quasi-normal modes. Of course, this sound is here exaggerated. They should be gravitational wave frequencies, and somehow if they are going to be detected, that LIGO may somehow the answer of it. But if we have a direct detection of them, the quasi-normal modes, automatically the gravitational waves will be proved. Not indirectly, but will be proved directly. But, sorry, I want to come to Constanter. He used this arithmetic invariant because in the large M limit, he has also used the more Sommerfeld quantization, and in the highly excited states, this arithmetic invariant approximated to n times h bar. But the answer that he got was showing difference from the Beck-Einstein, and he also stated that the Beck-Einstein quantum mechanical explanation for the minimum area change somehow is wrong. But later on, 5 years later, Meguiar said that, okay, instead of getting the real frequencies, the frequency of quasi-normal modes should be the combination of real and its imaginary mode. I mean, the absolute value of the omega frequency should be taken into account. And if you perturb the black hole, with a very high, that these normal modes are highly damped normal modes, the imaginary part becomes dominant than the oscillator part, I mean the real part. And he used this formulation of mathematic invariant of Constanter with the dominance of imaginary omega, and also instead of the frequency, he used a transition frequency. I mean, this is like, you know, in the Bohr atomic model, when the energy so we have subsequent energies. When an excited state goes one down, it emits radiation. In the atomic model, it is electromagnetic wave, but if you have a black hole, that will be quasi-normal mode. So if this energy difference, energy gap, is used in the adiabatic invariant formulation, he exactly get the minimum area change of the Beck-Einstein. And that study get too much citation of it, because after him, many different black holes have been tested, whether they are adaptable to Beck-Einstein conjecture or not. Then, but many of them use the standard quasi-normal modes. In 2014, the Shaharhod, getting an idea of new observations, cosmological observations, which are about the boson stars. Or neutron stars. It is assumed that the black holes are circled with clouds, and the waves cannot pass these clouds. They reflect it back. So somehow the black holes are gauged. And to define the boxed quasi-normal modes, instead of a standard quasi-normal modes boundary conditions, he used those conditions. First of all, near the horizon, we should have only ingoing waves. But at the clouds, the waves should be somehow totally absorbed or reflected back. I mean, at the clouds, all the waves should be terminated. To satisfy that, as we know from the electromagnetic theory or the other theories, he imposed two extra boundary conditions. One of them is the Richter type boundary condition, the other is the Neumann type boundary condition. We first used his idea to gauge stringy black hole, and we get a spectroscopy, but that was also static black hole, it was not a rotating one. Then, okay, I will come to this later. Then we said, okay, let's use it to rotating one. And at that moment, we were studying on Einstein-Maxwell dilaton axion theory of the filament. They gave a solution to that action. What we have here, this is a kind of, it's a kind of, not that, a Kerr black hole solution. But this rotating black hole is in a mixture of axion, dilaton, and electromagnetic waves. It has not its own charge. Somehow it has induced charge. We have a background charge because of its, the fields around it. And it gains a charge just because of the background, so not itself, so not zero charge limit. And without, and it has, because if you kill the charge, that space-time will be totally killed. So we have to keep the charge, background charge fixed. And their solution contains two horizons, inner and outer, like the Kerr one. But structure is totally different because, first of all, it is non-asymptotic. So it's a kind of local solution. So that was published in 2003. We considered this black hole because that axion and the dark, that axion and the dilaton are also the good members of the dark matter. So as we know, our cosmos are filled with the dark matter. So we have a kind of black hole rotating in a dark matter. So and over there we have electromagnetic field, we have dilaton, we have axion, and we calculated its angular velocity, its Hawking temperature. We get its entropy, we get its angular momentum. For what? Just to show that it's first of thermodynamics of the black hole is satisfied. Meanwhile, since it's non-asymptotically flat geometry, we have to use the Brown-York formalism to get its mass. And the M seen here is not the mass of this black hole. The mass of the black hole is that quasi-electron mass because, as I said earlier, this is a non-asymptotically flat background. And when we insert all these things, I mean, the mass coming from the Brown-York formalism, the temperature coming from the statistical Hawking temperature, the entropy coming from Bekenstein, angular velocity and the angular momentum, we see that the first law is satisfied. And we will use it in our computations. Okay, now, what we have done, for simplicity, we use the massless Klein-Gordon equation. And we attempt to solve. At that moment, I also thought it's more generalized version, and I considered the charge massive Klein-Gordon equation. And the first time, that nonlinear, very sophisticated and very lengthy equation have been solved exactly. And because when you get an exact solution, you can do more applications like gravity factor calculations, Hawking radiation calculations, resonant frequencies quantization. All have been also done here, but that study was before that one. Anyway, but this is as I said, this is a box quasi-normal mode computation, not the standard quasi-normal mode computations. We insert all these things into the massless Klein-Gordon equation. Then, after getting the radial equation by using the spherical part symmetries, we imposed that the spherical part is a spherical harmonics solution, and then we inserted that let's say ansatz. At the end of the day, we reduce this radial equation to that structure, and we read its effective potential. And this is known as the radial equation or a Schrödinger-like equation. We are familiar with such computations from the chapter serial. So by getting the experience over there, we reflect all our knowledge to that program. And this is the tortoise coordinate. We also get the exact solution of the integrated exactly. and we check the limits. When the R goes to infinity, goes to horizon, we have negative infinity, and when R goes to spatial infinity, we have positive infinity. Exactly the things that we are looking for to bring a tortoise coordinate. Okay, so how we computed the resonant frequencies? First of all, as hot did, we changed our variable to 1. To do this, the main reason of this variable change is the clouds are assumed to be very close to the horizon. So when we make such a transformation, near the horizon, all the y values will be very, very small. And that will have some benefits in the computations. And in terms of y, our metric function f has been redefined in that structure, so that if we apply the Taylor series, we got this. This is important. This tau y. I mean, our f will behave linearly, dependent on y. The tau will be r2 minus r1 over r0. R0 was a charge rotating linear that. And also our effective potential gets a simpler form. Here, the important thing is omega tilde will be the energy of the rotating waves that we already know it from curve. Anyway, that change will also affect my tortoise coordinate, and we get the near horizon form of the Zerrelli equation. Now our Zerrelli equation near the horizon behaves in that manner. This is very good because when we get this structure, we get its exact solution in terms of the Bessel function. We have the first kind of the Bessel function, the second kind of the Bessel function. And then we started to impose our conditions. First of all, near the horizon, we must have only ingoing wave. So what we have done, we have used the features of the first kind and the second kind of the Bessel functions for small variables. We inserted them here, and that exponential to the power minus I omega r star, this is our ingoing. The other one becomes the outgoing. We don't want the outgoing. We get rid of it. It likes, in a projectile motion, you get 2 times, but then one is the physical, the other is not. So you eliminate it by simply setting the d to the amplitude 0. We eliminate this one, and our physical solution will be expressed in terms of the first type of Bessel functions. Anyway, then we have now the waves going in, and also I have a cloud very close to the horizon, and I want these waves should be terminated at the cloud. Then we applied the Dirichlet boundary condition, so that should be 0. Okay, so if it is 0, by using some special function group like the Untitled Chapter, there are many properties of special functions. We use one of them, and since that one should be 0, we get a kind of relation here, which is in terms of the tangent. And the tangent has also approximated value in terms of the gamma functions. And we see that in order to make it 0, this tangent I omega pi should be that one. So this is a kind of special frequencies. It's a kind of that if it is, if this satisfied, that means the Dirichlet boundary condition will be obtained. So this is called the first solution of the box quasi-normal ones, because the other one will come from the Neumann boundary condition. And Neumann boundary condition, as you know, it requires a derivative. So at the place of the gauge or the mirror, terminology of the Hot, that must be 0. We get the derivative of our solution, and then by using some properties of the special functions, we got another kind of resonant frequency. If tangent I omega pi omega bar, but omega bar, don't put it omega minus m angular velocity. If it is satisfied, also the waves are being terminated at the cloud. So we have two types of solutions, but either from the Richter or the Neumann, the zeroth order resonant condition. This resonant here, I mean the waves, the frequencies which make our waves be vanished at the cloud. This is the first, that omegas should behave like this, because if it is minus I n, and the n would want to integer numbers, so the tangent becomes 0. Then we use the first order resonant condition. Then we generalize it to the higher order, but this is a kind of iteration method at the end of the day. And we got such a condition. I mean, if it is satisfied, if our frequency satisfies these conditions, the waves are completely boxed or gauged. Yes, this one, and here we have, don't forget, this part, sorry, was omega tilde over the kappa. The kappa comes here from, it is exactly the surface gravity, by the way. And we got the resonant frequency. Here, minus plus just characterizes, this is negative stands for the Richter, positive stands for the Neumann one. And we got the box quasi-normal modes. This is the characteristic resonance spectra. And for in generic case of the massless Gordon equation for rotating linear contours. But I am looking for the highly damped modes. So highly damped mode means the energies, states, I mean the ends, should be taken very large. So that term becomes dominant, because that will go. That will also be dominant. Of course, we will look at this, by the way, it's media, I forgot to write it here. And at the end, I will concentrate on it, imaginary part, because we look at the highly damped modes. So then when we take the transition frequency computation, we see that this change in the frequencies of the quasi-normal modes is nothing but the surface gravity. In other words, it's that in terms of the Hawking temperature. Now, by the way, this is the, you see the similarity, this is the standard quasi-normal modes that I have computed. So box quasi-normal modes and standard quasi-normal modes at the highly excited states, they behave same. Then this is the rotating version of the adiabatic invariant formulation, because normally the Maguire used the non-rotating one, but if you want to use the rotating one, you have to also add this term. So this is, according to the first law of thermodynamics, this one. So we have the transition frequency here, that should be NH bar, but that was also that was also related with the temperature. When you inserted everything in, you get that this is nothing, this will be gone. You will find just this horizon. So adiabatic invariance is proportional with, directly proportional with the entropy. So, and then at the highest states, the adiabatic invariant is quantized with the H bar. If you substitute everything over there, and knowing that the area is the 4 times of the entropy, you see that the minimum change of the area is 8 pi H bar. This is exactly the Beck-Einstein answer coming from the quantum mechanical studies. So, and this is the first application of rotating black hole in non-asymptotically flat to the Beck-Einstein conjecture. So that supports the Beck-Einstein conjecture very strongly. So areas are quantized. I mean, when let's say the black hole absorbs something, it's enlarging, or when it gives something, it's shrinking. It's not by random. It's not continuous. It should be discrete, like the atomic model. I mean, as you know, we have a spectrum of electromagnetic waves around the atom. So when the electrons are excited, they give a spectrum that waves are not continuous. So you see light, dark, something like this. So quasi-normal modes will be also somehow, I mean, the area or entropy, and also you can connect the entropy to the information. These are all quantized. Okay. And so what we have done here, this is the first time we show that in the literature that box quasi-normal modes can be also used to prove or to support the Bekenstein conjecture. Rather than using the standard quasi-normal modes, we use the box quasi-normal modes first time in the literature, and we prove that also satisfy the Bekenstein conjecture. Even in a very strange black hole, which is non-symmetrical slot rotating in a dark matter. But here we used the Masters-Klein equation, and we have also new questions that can be extended to other perturbations, because we just perturbed the black hole with a spin 0 particle. It just heated it, and we waited it vibrating. But that heater can be an electron, maybe. At that time we have to use the direct equation, or it can be a photon. We can use the Maxwell equation. It can be a massive boson, vector particle, Broca equation, and gravitinos. So or maybe we can use directly the Tolkovsky equations to see whether the spin may affect the Bekenstein conjecture or not, because even the Bekenstein is spin 0 in computations. So that was the questions. Maybe we may continue on this. So in the next speech, we have another publication that Gülnal is going to give. We will also compute the height of the cloud. What should be the height of the cloud, which is circling our planet? So that will be also present later by Gülnal. Okay. If you have any questions. Sorry? Okay. Thank you.
Pause.
Anyway, we will do it all together at the
Yes,
end.
sure. But
Yes.
individual.
Are there any parallels of what you explained with the James Hamiltonian? Or
No.
because I was thinking it seems like it's the same setup with you have some normal modes and you're trying to quantize the gravitational. If you try to quantize the gravitational waves, I would imagine you could use the same framework.
Maybe you may, some such things may happen in a phase space. This is PQ space. If you pass through the PQ space, maybe such works can be done also over there. Because that adiabatic invariant formulation, normally it is integral PD. So if you map the things that you did here to the Hamiltonian space, somehow you will get the same answer.
Okay.
But
And what was the other way that you said would be calculated?
well, here what we have done, without going to without applying too much quantum, this is semi-classical way. We just use the equations in the equation of the curved space-time, and we somehow made everything analytically without applying statistics, mechanics or not.
And you still get the 8 pi factor
Yes.
right?
Yes.
That's amazing. Yeah.
Of course, that study based on the Maguire one, that the PRL one, and at first he gave us the idea. If you ask me who was the great guy, this one. He published this one alone in the PRL, and that one first is show that the way you find from mechanics, quantum mechanics, can be obtained in a different approach. That's why it was PRL. Yes.
We defined omega theta, omega minus and capital omega. We assume that it's positive or
we allow it to be negative or zero.
You are talking about the super radiance, of course.
Or anything.
Of course, we assume that it's greater than zero. Yes.
It says that being quantized, I mean the area, surface area of the black hole is surprising, or the quanta which you wrote for the delta A. I mean, when we look at the first one, if we consider, as you said, if a black hole emits energy out, its surface changes. And it should be quantized, and that is very trivial because we know that the energy which comes out is also quantized. Energy was quantized 100 years ago. So then, if we
But the energy that you know was electromagnetic energy
that is
100 years ago, and this is the energy of the gravitational waves.
It doesn't matter. Energy, we can quantize it because we know it. So now then, if energy depends on, I mean, is related to the volume or surface or whatever, then that object also should be quantized. But exactly what is the quanta which you found here, I think that is more important than being only quantized. I mean, you found exactly the same answer. That is important.
Yes.
Not being quantized.
Yes, you are right. You are right, and this is in a, you know, if you take the hydrogen atom, of course, forget the time, these are all asymptotically flat curves, but that was the non-asymptotical flat, and even over there, somehow we get the same answer. That was the important.
That is what I say. I mean,
Yes.
the magnitude delta
Yes.
A is important.
Yes.
Otherwise, being quantized, I think this is very trivial. I mean,
But
it's not that
the
much.
quantization exactly matching with the inspiration of the Beck-Einstein.
Understood.
Yani, of course, the Beck-Einstein is
Ah.
is the head of this idea. The boss of this idea is the Beck-Einstein.
The father of science.
Yes. So that's being a great scientist. Your ideas, many years later, still being proven by different methods, because he exactly found the core concept, quantization of areas. And it seems simple, like E equals mc squared. But in many different methods, you come to the same conclusion. That is important, according.
That's true.
Yes.
Yeah, this might not be directly related to your work, but I wondered if you'd read a paper that came out a few months ago by Niayesh Afshordi, which ended up being quite controversial. He was claiming that you might be able to test for non-GR effects, looking at echoes of gravitational waves coming out of black hole mergers. I guess something you said kind of reminded me of that. So he was saying that if there's some kind of non-GR structure, it could cause this kind
I think
of
it was
thing.
written against LIGO, that's why.
Yes, yes. So I just wondered if you'd heard of that and you had any thoughts about that.
It's not related with this one because that mergering of black holes created high amplitude waves.
Yeah.
That's why we let's say observed it, detected. But that is needs a time maybe for the mankind, because we have to detect continuously the waves coming from the black hole. That will be the quasi-normal mode somehow. We will estimate what kind of black hole we have, because that frequencies actually include the characteristic of the black holes. And then if you take the difference in the energies, I mean transition, this time we can prove experimentally the black hole is quantized. That is it. I can guess what they are meaning, because they have still question mark whether they are the energies of the merger in black holes or something else, or just noise. I think they are a little bit different. But that needs a direct identification of waves. Well, I don't know whether the human being can be successful about it or not. Yes, any question?
Well, this is questionable. I have a method of quantization which does not fit Beck-Einstein. I am not sure whether it is correct. What do you mean here by quantizing area? I want to see quantization of the gravitational. If I have no black hole, forget about black hole, forget about the horizon. I am talking about waves, quantum waves, that relates to gravitational waves. So then that brings me to Price DeWitt and Richard Feynman, which did real quantum gravity.
Yeah.
But very special case, okay, area quantum, because geometry is part of gravity, true. So this concept is valid as long as you have a black hole horizon area. But as I said, far away from any black hole, still I have gravity waves. And I want to see whether that waves are quantized or not. So 1963, Acta Physica Polonica, Richard Feynman, the author, and 1968 Phys Rev, 3 very long papers by Price DeWitt, fathers of quantum gravity. I don't know. So it is open to discussion. We hope that in the future we shall see more things in this line and the real quantum gravity.
This was quantization around flat space.
That was in the first approximation. He tried in the flat space polarization of the gravitational wave. This was what Feynman did. So, as we talk about quantization of a photon, quantization of electromagnetic wave, so normally, that is why Feynman's approach was that. It was the real, because, you know, he discovered quantum electrodynamics with other colleagues. So he wanted to apply the same rule to gravity waves. So you have to identify the independent degrees of freedom. So for a photon, that is well known today, but for graviton, it has more components. So that has not been achieved. It is still open. But when we say quantum gravity has not been done, this is what is meant. So it is open. The difficulty, of course, is coming from the curveness of the space. If you have a flat space, then you can define a lot of things easily, but then you have space curved. You have technical problems, because each curved space creates new particles. So it violates particle conservation. But in a flat space, you don't have that. Only the field itself can create, annihilate something. So this is a very difficult problem. I don't have anything to say much.
Okay, thank you. Of course, the key point is quantum gravity. It's more deeper quantum than here. These are all somehow semi-classical. We partly use quantum, we partly use analytical solutions, and somehow we combine them. But the deepest, of course, it's more quantum mechanics. Then it is somehow we have to study more to reach over there. But we will not fed up. We will continue in the same line.
Interestingly, I had attended the lectures of Price DeWitt. He had a lecture on quantum gravity. Believe me, I took lecture notes for 2 semesters. I have never used in my life those lecture notes of Price DeWitt. I lost them even in my old office. Because why did not work on it? Nobody worked on this subject. You have to start from scratch. This is the fact. So they are very, very advanced level ideas and maybe real physics, but it is so difficult.
Yes. Okay, I think if you don't have any question, we can give the break.
Gelecek olarak